Right, we were dealing with homogeneous linear systems where we would just have this system and we said f of t is actually identically equal to 0. So these were the homogeneous systems. Now, in this case, we are saying uh, f of t is not 0. So we now have a non-homogeneous system. That f of t will then make the system non-homogeneous. So when we were dealing with first order, second order differential equations, non-homogeneous systems, we would solve them using the method of, especially the second order differential equations. The second order here, we would solve them using method of undetermined coefficients. Of t. So we would use method of undetermined coefficients provided this function had the form of exponential functions, the form of polynomials, the form of trig functions, and the different combinations. This is just a review of what you did in undergraduate ordinary differential equations course. So again, we needed the coefficients to be constant. So the A1, A2, and A0 were constant coefficients for the method of undetermined coefficients to work. So we can just borrow the same idea where we make sure that the coefficient function matrix here is actually constant. And f of t is a vector of either constants, polynomials, exponential functions, sines and cosines, the finite sums or product of these functions. Exactly in the same way we were dealing with the second order differential equations. We apply the same aspect on the non-homogeneous systems of first order differential equations. So, for example, here we have this non-homogeneous system, and here our f of t, you can write it in terms of the quadratic equations that we have there. So that's minus 2, 0 times t squared plus 1, 0, 1 times t plus 0, 5. So you can see it's a quadratic in terms of what? Of the t. It's a vector which with quadratic terms. So we can expand f of t and write it like that. And our worry is how do we determine the particular solution p using the form of f of t? How do you determine the particular solution for xp given the form of f of t? So this is represented by polynomials now. So basically, we need the generalized version of the polynomial vectors here. So we would then now have your xp having the general form. So you then say a1, b1 times t squared plus a2, b2 times t plus a3, b3. And then plug this back into the system and find the values of A1, B1, A2, B2, A3, B3. And after that, you would have found the particular solution. Remember, you would have solved for the homogeneous solution as well. So you still have to do the same thing. You solve the associated homogeneous system and then solve for the particular system and then uh, the solution will then be the complementary function plus xp, the particular solution. So that's exactly the same thing that you're doing. So you just need to do some bit of algebra on matrices when you plug xp back into the system. So whatever we're doing for the homogeneous case, we then now combine it with what we do for the non-homogeneous case, where we need to do further work on finding the particular solution. And it works only when the coefficient matrix is what? Is constant. It's a matrix of constant entries. Right. So let's see how this works out. So we have the associated homogeneous system. We are solving it. So we just go for the coefficient matrix and find the determinant of A minus lambda I, and we get a case of distinct eigenvalues. And now I trust that you can find the eigenvectors. Just cross-check if you can get these two eigenvectors associated with the eigenvalues. And then you have your complementary solution vectors. So complementary solution vector, which is the general solution using superposition principle. So that's how you deal with the homogeneous system. So now, remember, we unpegged f of t, and the f of t had the form of a quadratic polynomial. And we then put the generalized polynomial vectors, xp as a polynomial vector. So all we need now is to then remember we want to plug it back into this system where x is replaced by xp, and solve for A3, B3, B2, A2, and A1, B1. So if we differentiate, this is what we get. There's xp, and then we then substitute xp on the left-hand side, and then we substitute the xp on the right-hand side. And when we expand the right-hand side, we then now are able to come up with row by column A3 plus 3B3, row by column 3A3 plus B3 multiplied by T squared. We do the same matrix multiplies the next term, the same matrix. We'll multiply the other term, the three terms here. This is how we do it. And we cross-check that everything that we've done here is actually correct. And we are not forgetting that we have a term for f of t here that we add at the end, which is in expanded version, so that we can now bring like terms together, like terms together, like terms together. And after doing that, we will find we have 6 equations for the 6 unknowns. So take note that when you then now deal with systems, the method of undetermined coefficient becomes a cumbersome task. So, but we should solve for uh, all the unknown coefficients, the 6 of them. So at the end, after attempting to solve, this is what we get, and we just go back and plug them in, and we then have found our xp. And we then come back here and then say x in general is the complementary vector solution plus the particular vector solution, xp. And this now gives us our final our final solution. So now this is in general what you do. So if it's xp, if xp is in terms of the polynomial of the is in terms of the a trigonometric functions, you know, you have a combination of the trigonometric functions sine and cos as usual, and so forth and so forth. If it's exponential, you also just have a general form of exponential. So that's what we are now going to do here. Determine just the form of a particular solution. Remember, all the rules of linear independence should apply. So in other words, if, for example, e to the power 4t appears in f of t as well, then you need to make sure that if the xp has taken care of that for the function is linearly independent by multiplying by an additional t. But I will show you why that will then bring a different that will bring a different formalization. So, for example, if f of t is for e to the power 4 f 4t, and let's say f this was actually some x1 it contained, so let's just say k1 e to the power 4t, and in f of t we would have something like e to the power 4t times the sine t. All right. No, just say e to the power 4t there. 2 or minus 3 e to the power 4t, something like this. All right. So definitely f will be written as 2 minus 3 e to the power 4t. So we have e to the power 4t in the complementary solution and e to the power 4t in the non-homogeneous part. So naturally, from a second order differential equation, we would just say here in xp, naturally it was supposed to be a1 b1 e to the power 4t. So to make it linearly independent, we would then want to multiply by t in the case of the differential equation. But in this case, once you want to form a linearly dependent solution here, it's not just multiplying by t. We know t is a polynomial of order 1, so you would need to say xp1 would be a polynomial, so a1 or a2, a1, b1, t plus a naught, b naught. So you have to multiply this e to the power 4t and this guy here by the full generalized version of a linear vector. So your xp in this case would then be equal to a1 b1 t plus a naught b naught, and then you multiply it by e to the power 4t. And that's the difference between systems and the single second order differential equation where you just multiply by t and things will be fine. So this is the mere difference. Once you multiply by t or by t squared, you then need to put a full generalized version of a quadratic vector. And once you do that, then you are multiplied by the next by the other function. Let's see how this one works. So here it says determine the form of a particular solution vector xp for the system. Okay, what we will do is to investigate the complementary solution, even though we are just looking for xp. The reason being we want the functions that are xp to be linearly independent to functions that solution vectors that are in what? in the complementary vector solution. So let's look at the homogeneous system and then extract from this homogeneous system our coefficient matrix, and then we can find the eigenvalues, and we then look at what is in f of t. In f of t, we have e to the power minus t, and yet in xc, we have e to the power 4t and e to the power 2t. So since this eigenvalue uh, is -1, is different from 4 and 2, then there is no need to worry. The form of xp will just be determined by the generalized a form of e to the power, the vector with e to the power minus t. So if we are to write f of t, it's a combination of the exponential functions and the linear polynomials. So if we are to write it nicely, we can expand it to get -2 and 1 here times e to the power minus t, and then here we have 0, 0t, so it's 0 minus 5, and get multiplied by t, and then we have 1 and 7. So this is not division, by the way, it's just 1, 7. So this is the form of f of t. So using the method of undetermined coefficients, we'll then have a generalized version of this, which is just a3b3 times e to the power minus t. And then we want the generalized version of a linear polynomial, which is a2b2 times t plus a1b1. And this is the form. So it is based on the premise that xp should be linearly independent to xc. And then it's also determined by the fact that a f of t has the forms of exponential, trig, and polynomials. And once we have a polynomial, even if it was going to be f of t is equals to 1, 3t squared like this, in x of p as it were before, we would definitely use a full generalized version uh, of a quadratic polynomial. So that's how you do it. So this is the problem on method of undetermined coefficient. So now we're going to deal with another method, the method of variation of parameters, that you also might be aware of, and you have used it before. So definitely what we used to know, what we need to know is we have to find the solution of the homogeneous solution of the homogeneous system, the homogeneous linear system. And we are still trying to solve this system, the non-homogeneous system. So we know the general solution would be C1 times x1 plus C2 times x2 plus C3 times whatever up to Cn times xn. So now if you deliberately re-index the terms in x1 and x2 and xn, you can actually find that the general solution can be a system of the vectors, the eigenvectors multiplied by the unknown constant. So this system, this matrix with eigenvectors, no, of this matrix of solution vectors, not eigenvectors, of solution vectors, That's the combination of the eigenvector multiplied by the e to the power the lambda. So this one will be a combination of k1 e to the power lambda 1 of t. So it is a matrix which is not constant. It's not a constant matrix. So it's a matrix with functions of t. This is k2 e to the power lambda 2t, kn e to the power lambda n t. So that's what should happen here in that matrix. And this is the general solution which can be written in matrix form. And we collect this matrix and call it phi of t. So then we have our general solution written in matrix form as well. But we have a vector C here. This is the vector of unknowns. Unknowns. Okay. And remember x1, x2, xn, they form the fundamental set of solutions to the homogeneous equation or the homogeneous system. So the matrix that is formed from these vectors is now what we call a fundamental matrix. And we know it's non-singular. Why? Because the determinant of that matrix is actually the Wronskian of all the solution vectors, which we know is not zero because these solution vectors are linearly independent. So we are actually representing the system, the solution in matrix form. But in the matrix form, we can then extract the fundamental matrix, which is formed from the fundamental vectors solutions. And we are actually going to then say there is this phi of t satisfies the original equation. The original equation. Since phi of t is the solution fundamental matrix, it will satisfy the original equation where you just replace x by phi of t. It does satisfy. Okay? So these are just facts that are coming from the solution. We just visualizing the solution that we had. So for example, you then have this was, for example, you then say x is equals to c1 minus 1, 0, e to the power minus t plus c2 might be 1, 0 minus 1, e to the power 2t, something like this. So if you expand this as the solution, this was the general solution, for example, you are going to say this is equal to a minus c1 e to the power minus t, and then here it would be minus c2 e to the power 2t. So if you write it in matrix form, this will be minus 1, 0, 0, minus 1 times c1. Oh, no, that's not it. That's not what we want. So this is going to be equal to minus e to the power minus t, 0, 0, minus e to the power 2t, okay, times c1, a vector of c1. Okay, so what is then happening here is we can call phi of t is equal to minus e to the power minus t, 0, 0, e to the power minus, or e to the power plus 2t. And this will then become our fundamental matrix. You can see it's not constant. It's not formed of the of the eigenvectors. It's actually the solution vectors that come in there. And this is then what we then say our x will then be given by phi of t times c, where c is actually a vector of the unknowns c1 and c2. So we want to use that idea, saying our system can be represented in that system. And we have seen that since x is a solution, then if you then substitute a x bar, let's just see, if you say x prime, this is equal to phi prime of t times c. C is a constant. So if you then take this, remember if x prime is equal to ax, take this, replace this guy. So you have phi prime of t times c on the left-hand side, then x is equals to a times x, that's phi of t times c, right? And you can see that we can factor out t, the c there, and then we have phi of t is equals to a phi of t prime. So that's what we're saying. This solution with the fundamental matrix itself satisfies the homogeneous equation. That's what we wanted to show there. So now, remember with the method of variation of parameters for second order differential equation, we would say if the complementary solution was C1 y1 plus C2 y2, our yp was then going to be a u1 y1 plus u2 y2, where which were constants are now variables. Then variation of parameters, we can call them parameters. So that's the same thing. Instead, we had x is equals to phi of t times c, where this c is a constant vector. Now, just like Mena, we then now say, what if we change that to a variable vector, which is not a constant, u of t, which is just a column vector of functions u1 to un. So what is this u that we can use to substitute this and make x pizza with the formula, given that phi of t is coming from the homogeneous equation as the fundamental matrix of solution. So that's all. So we're now differentiating. Now you need to take care, this is an n by n, and then this is n by 1. So you need to make sure whenever these two are multiplying each other, a phi of t should always be on the left and the u on the right. Otherwise, if you swap it, then the matrix multiplication is not possible. All right. So we are now differentiating using the chain rule. So we started by differentiating u and then differentiating phi. So I now have phi p prime. And remember, if x prime is equals to ax plus f. So all I do now, I take this. We now have a new system here for finding the particular integral. So we substitute xp here, and then xp, remember we said xp is equals to phi of t times u of t. So we do the same here, and f of t remains. And now, because remember we said if x is equals to phi of t is the solution to the homogeneous equation, then phi of t satisfies the same homogeneous equation, a times phi of t. Okay, so wherever now we see phi prime of t, we can replace it with a times phi of t. And that's what we did here. Then the u remains. Now, what the net effect is, on the left-hand side, we have the same expressions, which will cancel to 0. And we will remain now with phi of t times u prime is equals to f of t. So we then have to pre-multiply by the inverse of phi of t on both sides. And this becomes I and remains with the u prime of t is equals to this guy here. And we will then find u of t by just integrating the outcome on the right-hand side. So we are now integrating vectors here, which are term by term matrices, vectors and matrices. You will then just integrate term by term. So your integration skills are now called to use here. And what it means is if you find the wrong phi of t, you also feed the wrong information into the particular integral. So then the particular integral will then be given by, remember, we had said xp is equals to phi of t times u of t. So we have found the u of t. We just have to then multiply it by phi of t to get the particular integral. Then the general solution is then given by the complementary solution, which is xc plus xp, directly by the method of what? Variation of parameters. So that's all you need to do. You need to know that the method of variation of parameters can do this directly without having to know the nature of f of t. And remember the method of undetermined coefficient, it becomes long. It becomes long when you, for example, just get f of t to be of the order t cubed. You have to then find like 8 unknowns. So that's even much worse. So we don't want that. We can do it far much faster and easier using the method of variation of parameters. We can also do it using the method of matrix exponentials, which I will introduce at some point. All right. So let's look at this example. Okay, we saw this example before. So I'm assuming that if we then start by solving the homogeneous solution, you will then see to it that a minus lambda I would be equal to 1 minus lambda 3, 3, 1 minus lambda equal to 0. So you have 1 minus lambda squared minus 9 is equal to 0. And if you are clever, you can now see that this can reduce to this kind of solution where you have lambda is equal to minus 2 and lambda is equals to 4, which is what we 4. And you get the eigenvectors associated with the 2 and as associated with the lambda scores 4 as 1, 1, associated with lambda minus 2 as minus 1, 1. And then after then writing this solution as x is equals to C1, 1, 1 e to the power 4 t plus C2 minus 1, 1 e to the power minus 2t, you then see to it that this could be e to the power 4t, e to the power 4t, minus e to the power minus 2t, e to the power minus 2t times C1, C2. So that we can identify our fundamental matrix phi of t from the solution. Okay? So now we have the fundamental matrix phi of t. We know that xp would be phi of t times the integral of phi inverse of t times f of t dt. So we then now want to find the inverse of this function. So it's 1 over the determinant. So what is the determinant of phi of t? This is equal to 4 times e to the power 2t plus e to the power 2t, which is what? Is that so? If you multiply your 4, no, is it 4? It's just 1. The determinant of this one was not. So this is e to the power 2t plus e to the, which is 2 e to the power 2t. So the inverse is 1 over e to the power 2t, which then gives us half e to the power minus 2t. Then you exchange this and then change the signs of those two. And at the end, you have this inverse matrix of the fundamental matrix of solutions. And sometimes I just prefer to keep the halves, the fractions outside if they're not really affecting anything inside the matrix. So the next thing is I now need to multiply phi inverse of t by f of t, which is that vector there. And that's what is happening. I'm now multiplying the two, and after some simplification, I then get the product as that. But remember, I need to integrate the product, right? Of phi inverse times f. And then I'm integrating, and then you do some integration by parts here, integration by parts on each of them, and see to it that you get something like this. Please verify that these computations are correct. And after that, now I can then multiply. So this half I kept it out because I didn't want it to mess what is inside. So I then have to multiply half times phi of t times the result from the integral to give me my a xp. And then my x will then be that phi of t times c plus whatever you get from here. So that would be xc plus xp. So yes, there is a lot of work that is to be done, but this is just directly without having to worry about calculating those unknown coefficients. So this is the method of variation of parameters. So you have to then now do more examples from the tutorials and master this.